Up to this point in the course, we've treated light, and in fact all types of electromagnetic radiation, as if they are waves. We'll see though that there are times where light seems to behave not like a wave but like a particle. And so the question is, what is light? Is it a wave or is it a particle? The other thing we're going to see in this video is that this wave-particle duality not only applies to electromagnetic radiation, but it also applies to matter. So for example, we think of an electron or a proton as particles, but we're going to see that they have wave-like properties as well. And so we'll try to get some understanding of how we deal with this wave-particle duality. Let's look at the experiment that first gave us an indication that light sometimes does not behave like a wave, but instead behaves like a particle. Now, before I get into that, let me just remind you that every experiment we've talked about so far in this course shows light to be a wave. In other words, we only were able to understand things like refraction and interference and diffraction by assuming light was a wave. So now let's look at the photoelectric effect. It turns out that when you take light and shine it on a piece of metal, electrons are emitted from the surface. Here is a schematic of the experimental setup to see this. You'll notice we have a piece of metal here, that's our plate P, and we're illuminating that with light. Also notice that we're doing this in a vacuum so that the electrons that are given off from the metal plate are not immediately absorbed by air molecules. Okay? And so because we have a vacuum there, what we find is that the electrons that are emitted from our plate P are going to come out, and some of those electrons are going to hit this electrode at point C. Now, because the electrode at point C is connected back to the plate, and because the plate is becoming positive as it loses electrons, electrons will be attracted back to that plate through the circuit. And so what we'll actually find is that we will measure a current in that circuit when we illuminate the metal plate with light. By the way, A here stands for ammeter, and an ammeter is simply how we measure current. So we illuminate that metal plate and we get a current flowing in the circuit. If we turn off the light, the current stops. If we think about this, it makes sense that if you shine light on a piece of metal, it would emit electrons, because we know that light carries energy, and any wave carries energy, and therefore if we can give enough energy to the electrons in the outer surface of the metal, those electrons can gain enough kinetic energy to escape from the metal. The amount of energy it takes to free an electron from a metal is called the work function of the metal. We use the Greek letter phi to represent that, and it's different for different metals. So some metals hold their electrons a little more tightly than others, but it turns out that it's a fairly small amount of energy that it takes to free one electron from the surface of the metal. And so we can see that it makes sense. We shine light on the metal, we're providing energy. Some of that energy is getting absorbed by the electrons, and that's what allows them to escape. What we now want to look at, though, is the details of that process. Let's first think about what the wave theory of light would predict for the photoelectric effect. The first thing you need to remember is that the energy of a wave is directly proportional to the amplitude squared. Let me just kind of remind you why that's the case. We know that in simple harmonic motion, the potential energy is 1/2 kx squared. And therefore, if we think about the total energy in anything that's oscillating, the total energy is 1/2 k a squared, where a is the amplitude. So the total energy of an object that's oscillating is proportional to the amplitude squared. Therefore, if that's true for the vibration that creates the wave, it's also true for the wave. And so that's how we know that the energy of a wave is directly proportional to the amplitude squared. So if you double the amplitude of a wave, it actually carries 4 times as much energy. So here's what we would expect from the wave theory. We would expect that the number of electrons that are emitted should depend on the amplitude of the light. So in other words, how much energy is the wave delivering? Well, that's proportional to the amplitude squared. So if we increase the amplitude or brightness of the light, more electrons should be given off. You'll also notice that the frequency of the light shouldn't matter at all, because fundamentally, the only thing that's affecting the amount of energy carried is the amplitude of the wave. So now let's look at a different theory. This was developed by Albert Einstein, and he developed this based on some work of other physicists that had been done at the time. So he didn't completely come up with this idea out of thin air, but he really put it in a new way. And what Einstein said is light can only be emitted in quantized amounts of energy, and he called those quanta. That's now what we call photons. So if you've heard of the idea that a photon is a particle of light, this is what it's actually talking about. Before we get into the rest of the details on the slide, I want to make sure you understand what we mean by saying that something is quantized. When we say that a quantity is quantized, what we mean is that there is a smallest amount of that material after which you can't go any smaller. So for example, think of water. If you have water, it seems like it's this continuous material, but if you kept taking half of what you have before and half again, eventually you're going to get down to where you just have one water molecule. And you can't go any smaller than that, otherwise it's not water anymore. And really, if you think about it, all matter is quantized, because fundamentally the smallest unit of any matter is the molecule or atom. Even atoms are quantized because fundamentally they're made up of individual electrons and protons. You can't have half a proton or half an electron. So that's the idea of quantization. Here's a new use of it though. We're saying that energy is quantized. Think about if kinetic energy were quantized when you're driving your car. It would mean you could go 20 miles per hour or 30 miles per hour or 40 miles per hour, but nothing in between. That's the idea of a quantum leap, which you may have heard of. And for those of you who have had chemistry, you know that energy levels in atoms are quantized. The electrons can't have any energy they want, they can only have specific values. Okay, so this is actually all related to that. Einstein said electromagnetic radiation in general, and visible light for sure, can only be emitted or absorbed in discrete amounts of energy called photons. And the energy of a photon is directly proportional to the frequency of the wave. The constant of proportionality is called Planck's constant. And it turns out Planck was the one who had done a lot of the work before Einstein that allowed him to come up with this conclusion. So, what does that mean for the photoelectric effect? Well, here's what Einstein said. He said that an electron is emitted from the surface of the metal when it absorbs a single photon. In other words, he pictured the interaction as being one electron in the surface of the metal absorbing one photon. And that's kind of how we usually draw photons. That electron absorbs the photon, and now it leaves the metal with a certain amount of kinetic energy. Now, how much kinetic energy will it leave with? Well, the maximum it can leave with is simply the energy that the photon delivers. Remember, E equals hf, minus how much energy it takes to get out of the metal, which is the work function, phi, as we talked about just a few minutes ago. So that's what he predicted. He said that the photoelectric effect is the interaction of one photon with one electron. Now, what's interesting about this, and where his predictions differ significantly from the classical wave theory, is that you'll notice if the frequency of our photon is too low, no electrons should be emitted, because at the very minimum, the photon has to carry enough energy to free the electron. So if the energy of the photon is less than the work function of the material, no electrons are going to be emitted. And that it doesn't matter how many photons you send down. So the greater the amplitude simply means more photons. But no individual photon can interact with an electron in a way that it will free that electron. Well, it turns out that it took a few years from when Einstein made his prediction until someone could really do a careful enough experiment to see this. And Robert Millikan, who you may have heard of in a chemistry class, he's the one who did the Millikan oil drop experiment that showed what the charge was on an electron. Anyway, he's the one who was able to perform this experiment. And what he found was that his experimental results agreed with Einstein's theory. In other words, when he plotted K max versus the frequency of the light, he got a straight line. And you'll notice that that's what we would expect. We said that K max is equal to HF minus phi. And of course, that's just an equation of the form y equals mx plus b. So in other words, you'll notice that the y-intercept would be negative phi, and the slope of this would be h. And so it turns out that Einstein was correct that when light interacts with metal, it is the interaction of individual photons with individual electrons in the surface that explain the photoelectric effect. So just like we can't explain interference and diffraction and refraction with thinking about light as being a particle, we have to use the wave theory. Here's an example of an experiment where we can only explain it by saying light is made up of particles. By the way, this was such an important experiment and theory that Einstein won the Nobel Prize in 1921, primarily for his work on the photoelectric effect, and Millikan won the Nobel Prize in 1923. So let's talk a little bit about these new things called photons. So what's the mass of a photon? Well, it turns out that photons are massless. So they don't have mass like an electron or a proton does. They are effectively pure energy. Photons have no charge, so they're neutral. And it's easy to see why that has to be the case. If photons carried charge, then just anytime you were in light, you would start to build a charge up on your body, and we know that doesn't happen. So photons are neutral. And most importantly, as we've said, we've seen that the energy of a photon depends on the frequency of the light. And by the way, you'll notice that this explains something that up to this point we haven't been able to explain using just the wave theory. And that is why higher frequency electromagnetic waves have more penetrating power. So for example, you know that visible light just bounces off your skin. But ultraviolet light, which has a higher frequency, penetrates deeper into your skin, and that's why ultraviolet light is responsible for skin cancer, because those higher energy photons can penetrate deeper into your skin. And of course, if we keep going up in the electromagnetic spectrum in frequency, we get to more and more dangerous forms of radiation. So in other words, when we get up to X-rays, we now have photons that have enough energy to penetrate your skin but are still stopped by your bones, which is why they're useful for diagnosing things like broken arms and etc. Then if we go up to gamma rays, those photons have so much energy that they can literally penetrate through just about anything. So that's something that we really couldn't explain before with just the wave model of light. I want to talk about the momentum and energy carried by photons. So if you remember the definition of momentum from first semester physics, you know that momentum is mass times velocity. Obviously, that can't be the way we define momentum for light because light photons are massless. But it turns out instead there's a different relationship for light, that the momentum of a photon is related to the energy of the photon. Okay? So in other words, we could write this, you'll notice that the momentum is hf over c. We could then take that and relate the momentum of the photon to the wavelength. Remember that since c is equal to lambda f, that means lambda is c over f, or 1 over lambda is f over c. So you'll notice that p is equal to h over lambda, or lambda is equal to h over p. Now, why do we care about that? Here's why we care. So far, we've talked about the fact that sometimes light seems to behave like a wave, and sometimes light behaves like a particle. Well, back in 1923, there was a graduate student named Louis de Broglie, and he argued that if light sometimes acts like a particle and sometimes like a wave, then maybe particles like electrons and protons, things that we've always thought about as just particles, maybe those also sometimes behave like waves. So here's what he did. He said, I know that for light, the relationship between the wavelength of light and the momentum is lambda is equal to h over p. And so he postulated that it would simply be the same for particles like electrons and protons. But now where p is our usual definition of momentum, m times v. Well, it turns out that he was right, and he won the Nobel Prize for this in 1929. So here's the question. What does it even mean to say that an electron sometimes acts like a wave and sometimes acts like a particle? What are we talking about here? Well, the way that we can show experimentally that an electron has wave-like properties is we can actually do the double-slit experiment with electrons instead of with visible light. So if you shine a beam of electrons at the appropriate sized double slit, you will actually get an interference pattern that is identical to what we would get for light. Remember that if we think of electrons as just particles and we shine our electron beam at our double slit, what we would expect is the electrons would only get here and here. But that's not what we find. We get a classic interference pattern for electrons in the exact same way that we do when we shine light at a double slit. Not only does the pattern look the same, the formula is identical. So if we calculate the wavelength of the electrons, as de Broglie did, and we know the separation of our slits, we find that the pattern is identical. So let's try to understand these results that we've just found. We've said that initially when we pictured light going through two slits, we pictured it as the interference of two wave sources. What we now know is that whether we do it with light or whether we do it with particles like electrons, in either case, we get an interference pattern. So one of the questions that you might think about is, well, what would happen if we only send one photon or one electron through the slits at the time? You're probably thinking, well, the interference pattern would disappear because the electron or the photon has to go through one slit or the other. It can't go through both. But it turns out that we still get the interference pattern even if we send one photon or one electron through the double slit at a time. Now, if we try to detect which slit we send the photon or electron through, or if we block one of the slits, then the interference pattern disappears. But if we simply send one photon or one electron through at a time, over time, we will build up the classic interference pattern. So in other words, it's kind of like the electrons or the photons somehow know where they're allowed to go on the screen, even though we think of the electron or photon as having to go through one or the other slit. Well, this seems like a real paradox, but it turns out that our modern understanding kind of gets rid of that paradox, of that question of can a photon or an electron go through go through both slits simultaneously. Here's our modern interpretation of the double-slit experiment. So first of all, if we want to predict where a particular photon is going to go, we get a probability distribution that's just based on that classical intensity pattern. So in other words, the brighter spots is where the photon is more likely to go. Same thing is true for electrons. It turns out that there's something called the Schrödinger equation that allows you to predict where the electrons will go. And some of you, if you've taken more advanced chemistry, you may have heard of the Schrödinger equation before. So we can predict where the photons or electrons will go. But the key thing to understand about this is that we can't predict where a particular photon or electron will go. And that's very different than what we had in the classic world, right? So think about the type of problems we did in Physics 1. You know, we take a cannonball and we shoot it at a particular initial velocity v0 at a particular angle theta naught, right? We can very precisely predict where that object is going to land. It's not that one time we shoot it and it lands over here, and another time we shoot it and it lands over here, over here. It always goes to the same place. So the macroscopic world is deterministic. But in the quantum world, it's not so simple. When we shine light through a double slit or electrons through a double slit, we can't predict where any particular electron or photon is going to end up. We simply know that the biggest probability is they'll end up in that central peak or the next peak over, and that probability goes down as we move out from the center. But we can no longer say this photon is going to go through there. So the way that we think about this now, the most modern interpretation of these experiments, is that electromagnetic fields and what we call matter fields, the fields that an electron or a proton would have, what we say is that those fields are quantized. So in other words, when we shine light through a double slit, even if ultimately only one photon is arriving at the screen, think about the wave as passing through both openings. But then only when that electromagnetic field interacts with the screen, at that point, it has to be quantized. So it has to deposit an amount of energy at one point, and that's what we interpret as a photon or as an electron. So it's a strange universe. That's all I can tell you. That these fields are quantized, meaning when an electromagnetic field or an electron field interacts, it has to do it in units of photons or electrons. By the way, again, if you've had more advanced chemistry, you've kind of seen this in action. If you can picture, like those electron cloud diagrams of the probability of where an electron is in the atom, that's really another example of what we're talking about here. Again, if something now interacts with that atom, it will interact with a particular electron, but it's not that we can locate that electron otherwise within that atom. So lots of interesting stuff here. This was really just my attempt to give you a brief introduction to some of these more modern topics in physics. And if you're really more interested in this, then you really need to go on into higher level physics courses where we get into it in more detail. And again, you also would see it in chemistry.